this video, we're going to talk about acceleration. So to start with, we have this formula. Average acceleration is equal to delta V over delta T. So in other words, just the change in velocity over change in time. And so one thing I want to note before we go any further is this arrow right here. And so these arrows denote that these quantities are vectors. So acceleration and velocity are both vector quantities, meaning that they have a magnitude and a direction. Magnitude is just the number associated with it, right? 45 miles per hour, 2 meters per second, or for acceleration, it might be 2 meters per second squared, different units, but it's just that number associated with it. So what's the direction then? Well, the direction is up or down, north or south, east or west. It could be positive or negative, forward or backward. And it just depends on how you define your coordinate system. You know, if you're given a problem with a car moving forward and you define this direction as positive and this direction is negative, then that's great. You can go about your problem that way. But you could equally define this direction as negative and this direction as positive. It does not matter. The physics will work out the same way. It will just change some minor details in your problem solving process, but it won't actually change any final answer. As long as you tell the reader of the problem or the grader which direction is positive, which is negative, or so on, then the person looking at your work can determine whether or not you did it correctly based on how you defined your directions. And so that's why that matters. And so now let's look at this example here. I have this V versus T graph, and it's a pretty bizarre V versus T graph, but you can see I've broken it into these segments, and this is a really useful problem solving technique for these types of problems, especially in Physics 1 when you're just starting out. And so break it into these different segments where the motion is uniform for that little segment. So that's uniform motion, uniform. How do you know it's uniform? Well, obviously this break right here is denoting that something changed, right? Something happened. So we're just going to look at the segments that are uniform, and we're going to use this average acceleration formula to figure out how to plot the A versus T graph down here. So looking at the first one, change in velocity over change in time, well, it goes from 5 all the way up to 15. So that's plus 10 meters per second in how long? 2 seconds. And so we have an average acceleration for that first segment of 5 meters per second squared. And so 5 meters per second squared, we can draw that flat line right there and go on to the next segment. So the next one, this is just a flat line. So this is super simple. This is going to be 0 meters per second squared for the slope here. There's no change in velocity. Yeah, the change in time is 3 seconds, but the velocity doesn't change. So we can go ahead and do that right on the axis there at 0. We can go on to the next segment. So for this next one, you see that we go from negative 15 down to, or sorry, from 15 down to 5. So that's going to be a decrease of negative 10, and it takes half a second. So negative 10 meters per second in 0.5 seconds is equal to negative 20 meters per second squared. And so we go over here, and for this half second segment here, we're at negative 20. I'll draw that a little bit nicer here. All right, close enough. So there you go. On to the next one, we go from 5 all the way up to 35, 5 to 35, so that's a jump of 30, and it takes 1.5 seconds, so that's going to be 30 meters per second, and 1.5 seconds is 20 meters per second squared. And so we go all the way from negative 20 up to positive 20. There you go. For the next segment, this one goes from 35 down to 15, so a decrease of 20. So we have to attribute that negative 20 meters per second in how long? 1 second. So we're all the way back down here. And so we'll draw that line, negative 20 meters per second squared. And then for the final segment, we go from negative 15 down to, or sorry, from 15 down to 5. So that's a decrease. We have negative 10 meters per second. In how long? 3 seconds. It's going to be 3.33 meters per second squared, but it's going to be negative. So here's negative 5 right here. So 3.33 is about there. And there you go. So 3.33, negative 3.33 meters per second squared. And then what we can do is we can go ahead and fill these in, not as solid lines, but as dashed lines to help our eyes kind of visualize the graph from one step to the next one. We're not going to use solid lines because solid lines would denote that the function is continuous. It's not. You have to actually pick up your pencil to get from one segment to the next. Sorry, wrong there. And so we can't have vertical lines on, these would be totally vertical lines. We can't have those because that would not be a proper function. Okay, so we draw these dashed lines instead. So moving on here, you might ask next, well, what's the average acceleration of the whole interval from 0 to 11 seconds? And so you do that, A average for the whole interval is going to be some change in velocity over 11 seconds, right? And what's the change in velocity? Well, v final is 5, v initial is 5, so the change in velocity is 0 meters per second, and that would lead to an average acceleration of 0 meters per second squared. And I'm going to put the vector symbol on top because technically this is the 0 vector. There's not much difference between 0 and the 0 vector, but the 0 vector is proper here because we are dealing with vector quantities. And so we can go into more detail on that, but we won't here. So 0 meters per second squared is the average acceleration in the whole interval. And so the question becomes, well, you know, how is that even useful, right? And the truth is it's really not. You know, whatever this is, maybe a vehicle or whatever else it is, this is some very strange motion, you know, this jumpiness to it. And then we're saying that the average acceleration of the whole interval is 0. I mean, that seems kind of like not a very good approximation, and it's not. You know, whenever you do A average, it's not great. And so that's why we have calculus. And so we go down to this formula here. The instantaneous acceleration is the limit as this denominator, delta t, goes to 0. So we can't have 0 in the denominator, but what if you had 0.000000001 in the denominator, right? So instead of taking, you know, segments that are 1 second, 2 seconds, 3 seconds long, instead of taking segments like that, what if we just took these really, really small segments along the entire graph? And that's what this formula is saying. And so in calculus speak, that's the derivative with respect to time, d dt, derivative with respect to time of velocity. All right, and so let's go ahead and actually solve something then. So get a different pen out here. So for this first example, let us just say that v of t is equal to t squared. Then what's a of t going to be? Well, a of t is going to be the derivative with respect to time of v of t is equal to 2 times t. That's just the power rule for derivatives. What you do is you take the 2 out front, and so you get 2 times t, and then the power, instead of 2, it's going to be 2 minus 1, or whatever it was before, you're just going to subtract 1. So 2 minus 1 is the 1 power, so we're not going to write that in, obviously, we assume that. And let's go ahead and graph these as well. I think that's going to be useful, but we're just going to do it qualitatively so that we can do it quickly. So t squared, that's going to be the right-hand side of a parabola there. I could draw the left-hand side, but it's not really useful in physics most of the time. So we'll just restrict it to the right-hand side. That's v versus t there. And then what this formula is telling us is that the acceleration with respect to time is 2t. Well, that's just a diagonal line, and it has a slope of 2. And so there you go. That's your velocity and acceleration graphs, just using some quick calculus. And so that's a lot faster than applying this average acceleration formula over and over and over again to all these different segments. You can just take the derivative with respect to time. So let's do another example here, example 2. Let's just suppose now that v of t is equal to 3t cubed plus 1/3 t squared minus t plus 204. Let's just say that. So what's a of t going to be? Well, a of t, we're going to bring down that power. 3 times 3 is 9. T raised to the power of 3 minus 1, so t squared, plus 2/3. Again, the 2 just multiply out front. T to the 2 minus 1 power is 1. Minus, so t then is going to go from, it has a 1 up here, right? And that 1 is going to go out front. And then t to the 1 minus 1 is 0, which is also 1. So this just becomes 1 here, plus 0. 204, you take the derivative with respect to time of a constant and you get 0. And so this whole last term doesn't even matter, right? And so there you go. There's your acceleration with respect to time. We just took the derivative. And now as a third example here, example 3, let's do if a of t. So we're not going to be given v of t every single time. So let's say that a of t is, 4t plus 27. Then what we want to do is say, okay, v of t then is equal to the integral of a of t with respect to time. And so again, this is more calculus. So if you're not familiar with this, you can hold off on this sort of step and come back later once you have some more calculus knowledge. But we're just going to take this integral. So the integral then of 4t plus 27 dt is equal to 4t squared over 2 plus 27t. And then we also need to add on a constant, because just as this 204 went away and became 0 when we took the derivative, we have to account for the fact that there may have been a constant when the derivative was, there may have been a constant before and then we lost it when we got to acceleration. So you always lose information. When you go from x versus t to v versus t, you're going to lose some information. When you go from v versus t to a versus t, you're going to lose some information. So we're accounting for what might have been lost. And that's what that constant is. So v of t then is equal to 2t squared plus 27t plus constant. And one more word to say about the constant while we're on this topic is that x of t, v of t, and a of t, these are all dependent on the reference frame that you're in. And so, for example, suppose that you're driving in some car and somebody on the street sees you and they say that you're going 50 miles per hour. But in the car, you're sitting still. And so everything that happens around you, you're not even driving. Let's just say that you're a passenger in the back seat. It wouldn't matter. It could apply to anyone. But let's just say that you're in the back seat, you're reading a book. The last thing that you're thinking about is this 50 miles per hour. For you, everything is 0 miles per hour. And so that's really what this constant is in reality. It's the idea that these different quantities, x of t, v of t, a of t, that they depend on the reference frame that you're in. If you're in a car and you're sitting still, you can claim that you have a velocity of 0 meters per second and everything around you has a velocity backward in this negative direction. Everything is just moving past you, but you're sitting still. Whereas the person on the street might claim that they are the one sitting still and you are the one moving at 50 miles per hour. And the truth is, in physics, there is no right answer. Both of these are equally valid things to say. And so that might sound counterintuitive to people just starting out in physics, but this is some of the most intriguing, one of the most intriguing aspects of physics is this idea of reference frames. And so don't blow it off just the first time you hear it. It takes some getting used to, but this idea of reference frames is powerful and it has huge implications, especially when you get to things like special relativity and the speed of light.